Irrational numbers. That's going to be the first lesson of Chapter 2, defining what are irrational numbers. Learning goals for today. First, understand the basic concept of irrational numbers and is able to use a calculator to estimate the approximate value of an irrational number. So I highly recommend you to go grab a calculator now because that's something we're going to be using with basic calculation later. So go grab a calculator that you probably have and we're going to start. Introduction. Liam is a freshman who has just entered 8th grade. One wicked morning, the engineer's father asked Liam a math problem. A square wooden board with a side length of 6 centimeters has 4 right triangles sawed off as shown in the figure. Please calculate the area of the remaining square planks. So this part right here is sawed off. So we only have that smaller square over here. How many centimeters are the sides of the remaining square planks? Have you seen this number before? Can you help Liam solve this problem? Now that's just something you can ponder with as we move into our lesson. This is when we come to the definition of irrational numbers. Now you probably not have heard of that before, but if you take off the "ir" at the beginning of irrational, you'll find that it just says rational numbers. So what can that mean? This is activity 1. Cut and piece together 2 small squares with side lengths of 1 and try to get a bigger square. Well, what you can do first is split it into half triangles and then put them together like this. And there's also so many other ways, like this way, this way, this way, this way, this way, this way. These are all different challenges. Different ways to solve this challenge. Now, here's a question. Suppose the side length of their large square is A. What condition does A satisfy? Okay. So because the area of the large rectangle equals 2, so A squared equals 2. So we do know that because this is the same square as before, so this has to equal 2, so then A squared equals 2. That makes sense. And just to point out why we used S, a large rectangle. Well, S is a mathematical, you could use any other number like F or O, but S, it's just a variable that in math we more commonly use to define area. So if you're wondering why it's not A, well, we use that for something else. So S is what we've chose to most likely use for area. So that's just something you could keep in mind. Challenge 1. What type of number is A? Can it be a whole number? Now I want you to ask yourself that question for a moment. Can it be a whole number? Well, because A squared equals 2, we already have that up here. And 1 squared equals 1, 2 squared equals 4. So 1 squared is less than A squared, which is less than 2 squared. So 1 is less than A, which is less than 2. So A is not a whole number. Now I want you to think about that for a moment. A is not a whole number. And its square is in between 1 and 4. A itself is in between 1 and 2. Just go over this for a moment. Does it make sense? It does? Okay, now we can move on. So, why don't we take a triangle ABC from this square? So, in triangle ABC, AC equals 1, BC equals 1, and AB equals A. So that's what we have. Yep, this is the same square. So according to the side length relationship of the triangle, so it says the sum of any two sides of a triangle is greater than the third side, or this difference of any two triangles is less than the third side. That's what each triangle should have. So then AC minus BC is less than A, which is less than AC plus BC. So 0 is less than A, which is less than 2, and A is less than 1, so A isn't a whole number either. Okay. Alright. Oh, and if you if you either haven't learned this or you skipped this video or you just don't know about this rule right here, I'm going to put it in the descriptions, or if you would like to further learn it, I can paste the link in the description below. So you can take a pause to look at that right now, or you can move on if you think you're ready. Activity 2. Can A be a fraction? So first, can A have a denominator of 2? Well, 1/2 squared would just be 1/4. 3 3/2 squared would just be 9/4. So we can't have a denominator of 2. So second, can A have a denominator of 3? Well, 1/3 squared is equal to 1/9. 2/3 squared is equal to 4/9. 4/3 squared is equal to 16/9. 5/3 squared is equal to 25/9. So that doesn't work either. What? Okay. Can A have a denominator of 4? So 5/4 squared is equal to 25/16. 7/4 squared is equal to 49/16. So that doesn't work. Now, what is the denominator of A? So here's a conclusion out of all of our observations. So A isn't an integer, neither a fraction. So if you go back to the definition of a rational number, A isn't a rational number. Isn't that strange? If you go back to the lessons we already covered probably in 7th grade, rational numbers is a number that can be written in fraction form. So A isn't a rational number. So here's our next question. How much is A? Well, as shown, what relationship holds between the side lengths of the three squares? Well, we do know that this has an area of 2. This has an area of 1. This has an area of 4. So what is an integer part of A? Do we know that? What is the 10th digit? What about the hundredths? What about the thousands? Complete the form below. And using the calculator you just collected from the beginning of this lesson, calculate if A is greater than 1 and less than 2, calculate A to the nearest whole number. And this is the area. Okay, so then the S would be greater than 1 but less than 4. Over here would be greater than 1.96 and less than 2.25. And it's starting to get thinner and thinner. But it seems like it keeps going on. So think, when the side length is calculated to a certain position, why is its square exactly equal to 2? Is A determinate, or what type of number is it? Well, A equals 1.41421356. It's a non-recurring decimal. So what is a non-recurring decimal? I'm just going to quickly cover that. A non-recurring decimal is a decimal that keeps going on forever, but there is no pattern to it. Or if there is a pattern, there is no repeating pattern. For example, okay, I'll give a few examples just in a moment. So estimate the side length of B of a square with an area of 5. Alright, so what this is asking you to do is, here is a square. It has an area of 5, so, and B is one of the side lengths, and this is a square. So what is the side length of B? to the hundredths place. So then b would equal 2.236067978 and keep going forever without any pattern. So it is also an infinite non-recurring decimal. Question 3. Use a calculator to calculate and write the following rational numbers in decimal form. What have you found? So all you have to do is just divide these, and then we'll see your result. So 3 would just equal 3.0, negative 3/5 equals negative 0.6, 47 over 8 equals 5.875, and so on. Oh, and these dots represent it's a pattern, so it keeps going on forever with a pattern. So in fact, any rational number can be written as a finite decimal or an infinite recurring decimal. Notice recurring decimal. Conversely, any finite decimal or an infinite recurring decimal is also a rational number. This is one of the key points that this lesson is trying to cover today. So write it down quickly in your this lesson's page in your notebook. All right, okay, now we can move on. So here's a key point summary. Non-recurring decimals are irrational numbers. For example, pi equals 3.1415926.5 and so on. And a decimal with 0 like this, 0.101001001, and then keeps going on with one more 1. There's one more 0 in turn between two 1s. That is non-recurring decimals. So this is an irrational number as well. Now practice. Example, which of the following numbers are rational numbers? What are irrational numbers? So there's 3.14, negative 4 over 3, 0.57, and 0.101010, and the number of zeros between two adjacent ones is increased by 2. Now we're going to do this together. So the rational numbers are 3.14, negative 4 over 3, and this is supposed to have that, and repeating 0.57. And just wanted to make sure, first, any fraction is a rational number because it's already written in fraction form, of course. 0.57, it's repeating, so with these dots. So, Papa, was it recording a video? Was it recording a video? Was that recording a video? And any decimal with these two dots in front of it means it's a recurring decimal, which means it definitely is a rational number. And 3.14, it's trying to remind you of pi, except that pi goes on forever, and this is just 3.14, so which means it is a rational number. The irrational numbers are just 0.101001 and so on. Here's some more training. Fill in the blanks. What are whole numbers, rational numbers, and irrational numbers from here? Alright, so the whole numbers are 0. The rational numbers are 22 over 7, negative 1/3, 0.3 repeating, and 0. 0 can be written as, for example, 0 over 1, so it is a rational number. Remember, 0 over 0 is invalid. You cannot have a denominator of 0. So yes, that rational numbers, 22 over 7. These are all fraction form, and 0.3, it is a recurring decimal. And some irrational numbers are just pi. So in conclusion, the examples of irrational numbers are numbers involving pi, or there is a certain pattern but an infinite decimal that does not circulate. So non-recurring decimals. Non-recurring decimals. The class summary for today. We learned all about irrational numbers and the concept of irrational numbers, and finding the approximate value of irrational numbers with a calculator. The two skills I hope you were able to learn today was understand the basic concept of irrational numbers and is able to use a calculator to estimate the approximate value of the irrational number. So I will leave the information from other lessons in the description below if you want to look at it, or feel free to move on to your next